Hi, Vicky.
Hi, Shane.
All right. I have to know. I don't know why I have to know, but I want to know.
I was up all
Are
last night thinking about this.
Yeah, exactly, and not just 3 minutes before we hopped on this call today. Are you a fan of Fleetwood Mac?
Fleetwood Mac. I really like Fleetwood Mac, but I feel like I haven't gotten fully into it. I have a real surface level love of Fleetwood Mac,
I was
popular
gonna,
songs.
that was a heck of a pregnant pause.
Yeah, well, I was trying to figure out how to say, because I like them a lot.
Sure.
I like them when I hear them.
Gotcha. See, I think like that's a good way of putting it. Yeah.
Yeah, and I have their albums, right?
Sure.
Um, but yeah, but I'm
Do
not
you
they're not my go-to.
Fair enough. Do you have a favorite song or songs that come to mind when you think of Fleetwood?
There's a lot, but I like Go Your Own Way. I like
Of course.
Gypsy, Landslide with
Of
like
course.
one quiet tear coming down
Oh,
your
that is very
cheek. Those. What
sweet.
about you? Do you like Fleetwood?
Yeah, I feel like my understanding or my familiarity with them is similar to yours. That
Yeah.
I don't know if I've heard a Fleetwood Mac song that I didn't like. In addition to the ones you mentioned, I like the Chain a lot. Has a really good like when the chorus
Oh,
hits,
the
it's really
chain.
driving. And for
Yeah.
legal reasons, people aren't hearing any of these things. They're gonna have to do some googling on their own. But yeah, I don't know. Like who doesn't like Fleetwood Mac?
Who doesn't like Fleetwood Mac? I don't know. You say you don't like the songs, but you had a really strong reaction to Tusk.
Oh, I didn't love Tusk. That's all I have to say about
I got
that.
to watch you. I got to watch you hear it for the first time in real time. It was like those YouTube videos.
There's a reason why this is an audio only medium. Science is fascinating. But don't just take my word for it. Join us as we hear stories from scientists for everyone. I'm Shane Hanlon,
And I'm Vicky Thompson.
and this is Third Pod from the Sun. Okay, so there is, as always, a reason why we muddled through a discussion about Fleetwood Mac. And so to help explain it, I'm going to bring in the producer for this episode, Molly Magid. Hi, Molly.
Hi, Shane.
Okay, so why Fleetwood Mac?
It's a good question. Their song,
That is the question.
Oh, I love the sigh. Like, all right, here we go.
I know, it's like everything that has gone on in my head I'm trying to explain. Okay, so their song, Landslide, has been stuck in my head the whole time I've been working on this episode because we'll be talking about landslides. And, I was also really partial to I Feel the Earth Move Under My Feet by Carole King.
Oh, that's a good one, but you can't just say it. You have to sing it. I'm not going to sing it.
Come on, Vicky, sing it.
I feel
Yeah,
the
come on.
earth move like that. You have to really.
Oh man,
Mm.
that was I can't. All right, so we're just keep powering through this. So beyond this kind of musical exploration of songs related to natural disasters, what you said landslides, but like what are we actually getting into today?
Well, we talked with Dr. Richard Iverson, who's a geologist studying landslides, how they move, and how to predict them.
And to remind everybody, this is part of our current mini-series where we talk to scientists who have written for AGU's science storytelling journal, Perspectives of Earth and Space Scientists.
Great, let's hear from Richard.
My name is Richard Iverson. I am a research scientist emeritus at the U.S. Geological Survey's Cascades Volcano Observatory.
And what is your research about?
In a single word, landslides, but that's a little bit simplistic. Really, what the great majority of my work is focused on is a type of high-speed landslide called debris flows, and then sort of their close relative debris avalanches. And the only real important difference between those two is that debris flows are generally saturated with water, and partly as a consequence of that, they're more mobile than debris avalanches. But both of them can move really fast, meaning hundreds of miles an hour in some circumstances, which of course makes them very significant hazards.
Can we back up just a little bit? I'm not sure I know what a landslide is. Could you explain it?
Well, a landslide is really any mass of earth material that moves down slope under the action of gravity. And so landslides range from those that move imperceptibly slowly. I've studied one slow-moving landslide that moves less than a meter a year on average. And that can continue for centuries or even millennia. And then at the other extreme are these high-speed kinds of landslides that happen abruptly, usually on big mountains, and in the case of the landslides I study, largely on volcanoes, but they can literally move hundreds of miles an hour. They happen at all scales and all speeds, and so there's a great diversity of things that we all lump together and call them landslides.
Okay, so that's interesting that there's such a range in landslide speed. I've only thought about the ones that happen really quickly and suddenly.
Right. Like Richard mentioned, ones that can last for centuries or millennia. I mean, that's incredibly slow.
Right. He said you wouldn't even be able to see that sort of landslide moving. You have to use special instruments to measure them and detect them.
So speaking of detecting and measuring landslides, like how does he do that?
Well, a lot of Richard's work has been around just how to do that, actually study landslides, because they can happen very abruptly.
You generally don't know when they're going to occur, and just as important, you really don't know how big they're going to be in advance. And so, if you take the research approach of, well, we'll set up equipment here in this locality, thinking we'll catch the next one, maybe the next one is 10 times bigger than you anticipated, and it simply sweeps all your equipment away. That's actually happened to me in one instance. Fortunately, we weren't there at the time, but it took all our equipment away. And so really, it's for that reason that a big part of my research career ended up being devoted to conducting experiments, lab-style experiments, but at a very large outdoor scale. And the beauty of doing controlled experiments is that we can control so many things about the landslide we're studying. We control its size, we control when it's going to happen, at least to a large degree. We control its composition, what kinds of sediments is it made of, how much water does it have in it, and so forth. And so that really, doing those kinds of experiments was sort of a major crux of my career, even though what attracted me to the field in the first place was the field experiences. That's always the exciting part for most geophysical scientists, is actually seeing the real thing out in the field.
So you're making a landslide in the field. I just can't wrap my head around that. What does that look like? What do you have to bring in to actually make them?
Sure. So the way we did it was we built a unique large-scale experimental facility. And so other people have triggered landslides in the field by taking a natural slope and adding water. That's the usual strategy to try to get it to go. We tried that as well, and it just didn't work out very well for us. And so we ended up building this big facility, which at the time was unique. Any place in the world, there was nothing like it. And it enabled us to, sort of manufacture a set of what in the mathematical world we call initial and boundary conditions, meaning we have all kinds of ways of constraining exactly what's going on at the onset of motion, the kind of surface the landslide will be moving across, its composition, and so forth. And that really allows us to sort of zero in on some important aspects of the process that would be very difficult to parse out just based on field observations or data.
So you're putting material into this machine or into this design thing? You put in like rocks and soil and water?
Yeah, so sure. We called this facility the debris flow flume, the USGS debris flow flume, and what it basically is just a big concrete chute on a steep hillside. And by big, I mean it's about 100 meters long. It's 2 meters wide, 1.2 meters deep, and it's steep. It's on a 31-degree slope. And 31 degrees is about the angle that, for example, a pile of sand would stand at if you make the pile of sand as steep as possible and then just let the sand sort of slide down on its own. That's about 31 degrees. It's pretty steep. It's steeper than most rooftops. It's steeper than most ski slopes. So it's not a trivial amount of slope to work on.
That sounds like the most extreme and fun playground slide.
Yeah, no, I mean, doing these experiments, which I was involved with for, well, really close to 30 years, it really is a lot of fun. There's an awful lot of hard work involved as well, because we're working with large masses of natural or close to natural earth materials, basically meaning, sand and rocks and mud and so forth. And you've got to get that stuff to the top of the slope. Typically, we'd use about 10 cubic meters. In some experiments, we'd use more than that, but 10 cubic meters is, many, many tons of material. And so we would haul it to the top of the slope using a dump truck and then load it using a front end loader, just sort of standard construction equipment. But then there was a whole lot of just, brute force shovel work that needed to be done as well to kind of get it positioned just the way we wanted, to install all of our instruments and so forth. So, I would often characterize these experiments as, 10 or 20 seconds of high drama and excitement packed into 2 or 3 days of work, so that the exciting part was over pretty quickly, but it could be really, really exciting when we let these things go.
Yeah, I can imagine watching them. It's just amazing. Do you have any fun or funny stories, either from those experiments or from the field?
Oh, yeah. I mean, there were lots of funny incidents over the years at the Flume, some of which were sort of contrived, some of which were downright scary and funny only in retrospect. I mean, one example of that was fairly early on, just a few years into our experimental work there. And we would have sort of a rotating crew. We had a core group of people who were there for pretty much every experiment, but then we'd have helpers who were there just now and then. And so one of these infrequent helpers we'd positioned out at the foot of the flume in what we called the run-out area to simply videotape this big, high-speed flow coming down. And because he didn't have experience working at the flume, I think he didn't have a real appreciation of just how fast this thing would be coming. And because he was watching it through the viewfinder of a video camera, trying to track the moving front, he didn't really appreciate how rapidly it was approaching him. And so basically the thing overran him. It knocked him down. His humorous characterization of the after effect was that every orifice of his body was filled with mud. It knocked him down, and what was most serious is that it broke his glasses, and a piece of glass got into his eye. And so I had to rush him to the nearest hospital, which was about an hour's drive away down in Springfield, Oregon. And fortunately, at the hospital, they were able to get the glass out and so on. But it was still a pretty traumatizing experience, and one that, that we learned from. And we had some other near misses, but I'm also just thinking of some sort of stunts that were, or practical jokes that were played on me. I remember once we had a film crew there, and over the years we had quite a few film crews at the Flume because it was an exciting thing to watch. And this particular crew was making a children's program. I don't remember the name of it. It was some sort of a science program really aimed at young kids. And they had this childhood star of the program. I think her name may have been Vanessa, but I'm not certain about that. Anyway, I was working at the top of the flume, where I always was when we ran these experiments, because I would always, kind of do the final check to make sure everything was ready at the top before we let this thing rush down the slope. And so it was sort of all systems go, and I gave the go ahead, and the switch was flipped, and down rushes the debris flow. And now I look down at the foot of the flume, and here's this person standing right at the mouth of the flume and just not moving, just standing there stock still, like waiting for this thing to come down. And I screamed at the top of my lungs. They probably heard it in the next county. And then I was just horrified to see this person just being not only overrun by the debris flow, but just knocked, a long distance into the air and so forth. Well, it turned out that what they had done is they had put a dummy at the foot of the flume just to make exciting video, I guess, and did not disclose that to me. And so that was a moment of terror on my part when I saw that happen.
Oh my gosh. Oh, I can't get this picture out of my head. It's imagining him screaming, "No, Vanessa!" just like at the dummy.
Yeah, I wonder if I could find a clip of that episode. I want to know more about it.
We'll do some YouTubing and see what we can find.
Yeah, same. That would be so funny. But in all seriousness, if it was a real person, that would make for a pretty traumatizing episode of kids' TV.
Oh, that's true. I guess rocks hurtling towards you at hundreds of miles an hour. That's not funny.
Yeah, definitely. But Richard often says people do underestimate how dangerous landslides can be.
Particularly if people have been living at the foot of a mountain somewhere and they've maybe been part of a family that's been living there for generations and nothing as bad has happened, and so they think of the mountain as being just a stable part of the environment that's really never going to change much. But then something happens, and it might be a dramatic trigger like a big earthquake, but it could also be really no perceptible trigger that things just get weaker with time and then eventually give way. So yes, people often do underestimate the threat. And one really dramatic example of that in my experience was the Oso landslide in northern Washington state back in 2014, which was a case where there was really by the standards of Washington state, not a very steep slope, not a very tall slope, only about 180 meters high. And it had been chronically unstable for many years. And people who lived at the foot of that slope were aware of that chronic instability, but it had always just been kind of I guess what I'd call a nuisance, in the sense that it caused a little bit of minor flooding. Some debris would come down and partly cross the adjacent river and cause some water to back up, but never a need for people really to evacuate or anything like that. It was just a nuisance. And then when the Oso landslide happened in March of 2014, it was not only much larger, but also much, much faster than anything that had ever happened there before. And it just, the results were devastating. It was the deadliest landslide in the history of the United States, with the exception of one event that occurred in Puerto Rico back, I believe, in the 1970s.
How do you communicate with people to try to get them to understand that significance?
In terms of communicating, that's really been a big part of my career, and something we finished just this last spring, was a big report on forecasting the behavior of lahars, which are very large volcanic debris flows, basically, coming down from the west side of Mount Rainier. And the west side of Mount Rainier is known to be an unstable or potentially unstable sector of Mount Rainier. And so in that case, we developed a very detailed numerical model of this process and created not only lots of still graphics, but also animations or movies of kind of the animated view of these simulation results. And those movies really, for a lot of people, things that are difficult for them to grasp just looking at a map, for example, and certainly looking at something like a table of data, seeing those animations where it really looks like the real thing, really, I think is an effective tool for communicating the nature of the hazards. And in some respects, it can scare people, but it can also edify people in other respects, just because it gives them a much more realistic impression of what could happen. I mean, it reminds me a little bit of when I was a young kid. I was interested in dinosaurs, and I remember hearing adults tell me, you just can't possibly imagine how big these dinosaurs were. And so in my mind, I developed this picture of the single footprint of a dinosaur covering, the entire state of Iowa where I grew up, or something. I mean, that's what I imagined when they said, you just can't possibly imagine. And of course, I think the same thing can happen with regard to some of these destructive geophysical events that, Yeah, they can be big and bad, but putting constraints on that and providing people with real information and movies where they can sort of see something play out in real time, is really effective at communicating the nature of the hazard.
Yes. Yeah, this is what communication's all about. This is why we do this, Vicky, such important work.
Such important work. Great reverence. But I think anyone who's listening to the podcast is probably pretty interested in science communication, so they know what you're talking about as well.
Right. Okay. So we know that communication is really important, but what else can be done to mitigate or prevent landslides?
Well, for the most part, we can't really prevent landslides, except in rare instances where there's some very high value structure that we know is in potential jeopardy. And so, to give you an example, I really can't think of a particularly good example in this country, but in Japan, which is a country with a much higher population density, of course, and also is almost entirely mountainous, there are locations where they've gone to extraordinary measures, to try to stabilize slopes. And, one approach is to simply drain them, to do a bunch of drilling and install various kinds of drains and maybe even pump water out. You can also build structural supports, to help hold it in place. Now that happens in this country too, but generally on a much smaller scale, with small landslides along highways and that sort of thing. But for the really big landslides, there's really nothing we can do to prevent them. And so it really becomes more a matter of trying to forecast what might happen and what the probability of that event might be. And the probability is a really tough one because unlike earthquakes, for example, which recur on the same faults over and over again, a classic example being the San Andreas fault, landslides, the really big ones anyway, don't recur over and over again on a time scale that really means very much to humans. Maybe the same volcano flank fails once every 100,000 years, but 100,000 years is a number that humans have a hard time, dealing with.
Yeah, that's interesting. So it's more about just trying to predict and make sure that people are aware of the landslide risk, and hopefully there aren't big structures or things in the way that could cause a big disaster.
Yeah, and I think, you just mentioned big structures in the way. Obviously a better understanding of the hazard can provide guidance for where you want to situate crucial infrastructure or expensive structures or whatever to try to minimize how much they're jeopardized.
That makes a lot of sense. So I know you've had a career that has spanned decades and you're continuing your career, obviously, but I'm curious, what are you most proud of?
I think what I'm most proud of in my career is two things that kind of go hand in hand. One was the fact that we created and successfully operated the debris flow flume, which to this day is a unique facility anywhere in the world. And that really went remarkably well. And the thing is, there was a lot of risk involved at the front end of that, because there was certainly no guarantee that we were going to be able to make this work and successfully create debris flows and landslides that helped us learn things about natural events. But that did work out, and I'm really pleased that it did, and also the fact that it enabled lots of other people to be involved with that work, and that has now kind of propagated and is carrying down to a new generation of researchers and so forth. And then hand in hand with that, along with all of the experiments, the whole time I was working on development of mathematical models to simulate these events. And as it's turned out, that has paid nice dividends as well, because the model, beginning about 8 years ago, really reached a point of fruition where it really became a useful, practical tool. And so now we really are using that model to make real-world hazard assessments and and to create these animations that we can show to people to help them understand the nature of the hazard and so forth. And so I feel really good about the fact that the work has had a real practical application.
What is the most fun or exciting part of your work?
Well, I would say the most fun part. So right now I'm involved in a little consulting project just here on my local mountain, Mount Hood, which I can see right outside my window here. And what's fun about that is just going out and so the issue there concerns potential hazards to a dam that's going to be rebuilt downstream from the north side of Mount Hood. And so the question is, what is the likelihood that some sort of big flow event, a landslide or a lahar or something, could impact that dam? And what's fun about that is I basically get to go out and hike around and kind of draw on all my prior experience to kind of, put this into some rather, compact and coherent package to explain to people, what the issues are or are not in that location. And that's just, it's fun and it's gratifying. I mean, that's not the most exciting part. The most exciting part was when we were making original discoveries at the debris flow flume and literally learning things that nobody had ever learned before. And anytime you feel that you've managed to do that you've had an insight that no one, to your knowledge, has had before, that's just a real source of excitement.
Yeah, absolutely. Could you tell me in 1 or 2 sentences why your research is so important?
I think the research that we've done and others have done on landslide and debris flow dynamics is important because of the role that it can play in informing people of what hazards are and then taking necessary steps to reduce people and properties' vulnerability to those hazards.
Yeah, at the end of the day, it's about the people.
Right.
That's a really nice sentiment.
Yeah, it's just like this podcast. We're all about the people as well.
You're really on your soapbox today.
I don't know what to say, and I don't know. Something just about Fleetwood Mac just puts me in the mood.
Ooh.
Oh man, I did not realize I was going to bring this energy into the episode. I guess all I can really say now is I think I'm going to have to go my own way.
Oh.
Go your own way. Yeah, see, Vicky, you did it before.
Shane, you have such a beautiful singing voice.
Oh yeah, my awful falsetto. Yeah, we'll just we will leave things there for now. And so that is all from Third Pod from the Sun.
Thanks so much to Molly for bringing us this story and to Richard for sharing his work with us.
This episode was produced by Molly with audio engineering from Collin Warren. Artwork by Jace Steiner.
And we'd love to hear your thoughts on the podcast. Please rate and review us. And you can find new episodes on your favorite podcasting app or at thirdpodfromthesun.com.
Thanks all, and we'll see you next week.
Can you hear them upstairs now?
No?
Okay, because everyone is home upstairs.
Oh, what are they
loud.
doing? Are they like having a dance party? Are they listening to Fleetwood Mac?
Probably.
Yeah?
Yeah.
What would be the Fleetwood Mac song that they would dance to?
Well, definitely Go Your Own Way. But
Definitely Go Your Own Way,
Gypsy,
right?
I feel like it's a good one. Especially
Which one?
Gypsy.
Oh yeah, Gypsy would be good.
Yeah, because it's like for Olivia, like anything that she could get like a good spin going. For my daughter, that's a good one.
I feel like we were looking at the videos beforehand.
Mm-hmm.
I feel like the Gypsy video is kind of whimsical as well.
Well, everything that Stevie Nicks wears is like scarves and like lots of things that flow.
Fair. Is that your daughter's aesthetic?
Yeah. I mean, when dancing, for sure.
When dance, like she has a
She'll
specific
be like,
outfit she puts on for
well,
dancing.
yeah, she'll be like, pause this, and she'll run in the other room and get on like a dancing outfit.
That is amazing.
And then be like, okay, ready.
Oh, I love
Starting
that.
again. Yeah.
Oh.
She's a little Stevie.